Hi friends, so welcome back to the course. So we would, I just kind of set up the physics or the basic fundamental equation for which will be pretty useful in deriving the one-dimensional heat equation. So this equation is called the Fourier's equation. Uh, uh, this equation is called the Fourier's heat equation. Actually, it relates the heat flux. This is called the heat flux, the rate at which the heat energy is getting transferred per unit area. It is depending on the thermal conductivity as well as the thermal gradient we call the rate at which temperature is changing. So I hope you are able to appreciate why this minus sign is here. See, in this case, heat flows in this direction, right? Heat flows in the direction from the point at which the temperature is 100 degrees Celsius to the point at which the temperature is 30 degrees Celsius. Here, if you calculate the dt by dx, let's say if I have a straight line like this, then obviously my dt by dx is decreasing, right? So this value in this particular expression will be negative. So with the help of this particular minus sign, we are able to tell that heat flows in this direction, that qx will be positive, which means that the heat is flowing in the x direction. So hope that makes sense. Now a few things to note. There is a slight notation change in the coming lectures. Here I have used T for temperature. Now in all the coming lectures, we will be referring to temperature with this particular notation U. Okay. Now the next question. Why we need PDE is this particular question. Why we need partial differential equation to solve this problem? See, actually what we are trying to figure out here. So we know that the temperature at this point is 100 degrees Celsius and the temperature at this point is 30 degrees Celsius. So satisfying these two conditions, the temperature distribution in the bar, in this particular bar, can have this form, or it can have this form, or it can have this form as well. So how it is actually varying? So the temperature is definitely a function of x. So it varies with respect to x. And moreover, temperature is also varying with respect to time. Let's say I'm starting this experiment at 10 a.m. where the temperature at this point is 100 degrees Celsius and the temperature at this point is 30 degrees Celsius. But now this at that particular time, let's say the temperature profile along the x direction was something like this, where this is 100 and this is 30, but this is u. But this won't be the case after like say 10 to 15 seconds, or let's say if I take the measurement at 10:30 a.m., this won't be the temperature profile within this bar. It will change. So the temperature is a function of u, which is the temperature. It's a function of both x as well as t. Okay, so you are trying to figure out the temperature, which is a function of two variables. So that's why you need partial differential equations, because if it was just dependent upon only one particular quantity, let's say x only, as in the case of a steady state heat conduction, which we won't get into. So since in this particular situation the temperature is dependent on both x and t, we need partial differential equations to solve this. See, at the it's not like actually we will embark upon some basic physical principles to derive this partial differential equation. So it's not like we are aiming for a partial differential equation. It is more of we are trying to solve a physical problem using a very basic physical principles like conservation of energy. Then at the end of embarking such a principle like conservation of energy, we will end up with partial differential equations. So that's how we will reach partial differential equations. So this is the physical problem. Now we have to embark upon certain basic physical principles to get to the partial differential equation. Then we will solve it. Thanks. We will look into more details in the next lecture. Thanks for listening.